Instagram. My handle is post_silicon. Right. Today, at the end of this lesson, you should be able to know what refraction is, critical angle and total internal refraction. And you should be able to know what is 2D and 3D wavefronts, diffraction. So remember that the speed of light is constant when passing through a medium and having a maximum value of 3 × 10⁸ meters per second in vacuum. So meaning that in other media, it might be slow, but in vacuum, it's traveling at a speed of 3 × 10⁸ meters per second. That's the speed of light. So refraction of light is the change of direction of light ray due to the change in speed when light travels from one medium into the other one of different optical density. So for refraction to take place, light have to travel from a medium of different optical density, from one medium to the other one of different optical density. So there has to be change in direction due to change in speed. So remember that the speed of light also depends on the medium on which it is traveling. Right, optical density is a measure of refraction power of the medium. So meaning that the higher the optical density, the more the light will be refracted, or it will be slowed down as it moves through the media. For instance, because glass is having high optical density than air, light will travel much slower in glass compared to air. Right, refractive index is represented by the letter N. A refractive index of a material is a ratio of speed of light in vacuum to the speed of light in material. So N will be given by C, which is speed of light in vacuum, over V, which is speed of light in a particular material. So that's the refractive index of a material. Right, materials with high refractive index will also have high optical density. So the normal is the line that is perpendicular to the surface, meaning that if this is the surface, this will be the normal. It will be the imaginary line drawn perpendicular to the surface, at right angle to the surface. Right. The angle of incidence will be the angle between the normal and the surface. Sorry, it will. The angle of incidence is the angle between the normal to the surface and the incident light ray. So, for instance, here, this is the normal to the surface, and this is the incident light ray. So this will be the angle of incidence. So the angle of incidence is the angle between the normal to the surface and the incident light ray. Right. Also, you need to remember the angle of refraction is the angle between the normal to the surface and the refracted ray. So it is the angle between the normal to the surface and the refracted ray. This is the refracted ray. Right. Theta I is the angle of incident, and then theta R is the angle of refraction. Right, let's remember Snell's law. Snell's law is simply stated that it is the ratio of the sine of the angle of incidence in one media to the sine of the angle of refraction in the other media is constant. So that is Snell's law. According to Snell's law, the ratio of the sine of angle of incidence in one media to the sine of angle of refraction in the other medium is constant. So let's represent that mathematically. So the ratio of sine of angle, sorry, the ratio of sine of angle of incident in one media to the angle of refraction, to the sine of angle of refraction in the other media is constant. This is a constant. Remember, this is representing the ratio of the refractive index of different material. So the sine of angle of incident in one material is equals over the sine of incident of the sine of angle of refraction in one material will be constant. So let's represent it the other way around. So N1 here, which is the refractive index of the first material multiplied by sine of angle of incident equals to this refractive index of the second material multiplied by the sine of angle of refraction. This is this theta 2 is angle of refraction. Or we may represent it this way. So say angle sine of angle of incident in one material over sine of angle of refraction in the other material equals to is constant. So it will be given by the refractive index of the material in which light is refracted, and then over the refractive index of the material in which that the incident, the ray came from. So we can also rearrange the equation this way. So now we can use this formula to calculate a refractive index of material. So it will be used, refractive index of material will be equals to the sine of angle of incident over the sine of angle of refraction. So in here, normally it is, this can be used to determine the refractive index of an optical media for a ray traveling from vacuum or from air to that media. Right, law of refraction. The law of refraction simply says that the angle of incident is equal to the angle of refraction. So let's just, when light is reflected, hello?
Mosala, one of the learners posed a question, is the refracted ray the original ray reflected by the medium?
Yes, come again with the question?
Is the refracted ray the original ray reflected by the medium?
Refracted ray, remember what we said about refraction. We said refraction is the bending of, let me just go to the definition. Refraction is of light is the change of direction of light ray due to the change in speed when it travels from one medium to the other medium of different optical density. So let's look at the diagram here. So a refracted ray is the same ray, but as it moves from a material of like air to water, and water will be having different refractive index. So it will be having different optical density. So the light will be refracted. The light ray will be refracted. So it's the same light ray, but it changes direction as it is being slowed down because it is entering the material of different optical density. It is entering the material of different optical density. So it moves from air to water with different optical density. So it will bend towards the normal. It will be refracted towards the normal. Right, we are still busy talking about law of reflection. So law of reflection, we are saying that when light is reflected, the angle of incidence is always equals to the angle of reflection. Here is not reflection, it is reflection. Reflection, it means it is being sent back, right? Now, angle of reflection is the angle between the normal and the reflecting surface and the reflected ray. So is the angle between the normal to the reflecting surface and the reflected light ray. So here you are having the normal to the surface, which is always at right angle to the surface. Now the angle of reflection will be the angle between the normal and the reflected ray. This is the reflected ray. It is being sent back. So this one, you already know it, that is the angle of incident. This R will be angle of reflection. Right, let's talk about critical angle and total internal reflection. So the critical angle will be, so before we talk about the total, the critical angle, let's talk about total internal reflection. So we are saying total internal reflection occurs when a light ray does not emerge from one media, but it is reflected back into the media. So let's look for the condition required for total internal reflection to take place. Light must travel from an optically denser medium, that is medium with higher refractive index, to an optically less dense medium, that is medium with lower refractive index. So angle of incidence in an optically denser medium must be greater than the critical angle. So two conditions for reflection, total internal reflection to take place. So remember that we are saying total reflection take place when when refracted ray does not emerge from the media, but is refracted back to the media. So there are two conditions for this to take place. The first condition is that light must be traveling from an optically denser medium to an optically lesser medium. For instance, if light is traveling from water to air, then total internal reflection can occur. But the second condition that must be met is that the angle of incidence must, in an optically denser medium, must be greater than the critical angle. And now let's ask ourselves, what is this critical angle? The critical angle is the angle of incidence in an optically denser medium, for which the angle of refraction in an optically less medium is 90 degrees. Right, if you look here, let's consider this green light. This is the angle of incidence, and this will be the angle of refraction. So the green light, you can see that the light ray represented by it's not the green light, but it's a light ray represented by the color green, just to distinguish between the different scenarios. So this one, it will go through. Why? Because this angle of incidence is less than the critical angle. Right. So what is a critical angle? A critical angle is the angle of incidence whose angle of refraction is 90 degrees. So meaning that this side, this line, and the normal will also be 90 degrees. So now, if you look at the light ray represented by a blue color, it is reflected back to the glass as it tried to move into the air. So what is the reason for that? The reason for that is that this angle over here is larger. The angle of incidence for this light represented by a color blue is larger than the critical angle. So the angle between the normal and this light ray is greater than the critical angle. So that is why this light is reflected back into the medium from which it comes from. So remember, what are the conditions for total internal reflection? Is that number one, light must be traveling from an optically denser medium to a less optically denser medium. So here the condition is met because glass is optically denser than air. So light was trying to travel from an optically denser medium, which is glass, to air, which is less optically denser compared to glass. Now, the second condition is that the angle of incidence must be greater than the critical angle. So this angle is greater than the critical angle because this is the critical angle. So this one here is greater than the angle of incidence must be greater than the critical angle. Hence, it is reflected back into glass. So total internal reflection occurs. Right. So there are application of total internal reflection, or it is mainly using optical fibers.
Musala?
So it is, hello?
Sorry about that. There's a student asking, what is a refractive index?
Refractive index, let's go back to our definition of refractive index.
Thank you.
Okay, refractive index of a material is a ratio of speed of light in vacuum to the speed of light in material. So that is the refractive index. So it is this ratio, it's given by the letter N, and it is this ratio, the ratio of speed of light in vacuum to the ratio of speed of light in vacuum to the speed of light in material given by a letter V. So refractive index is simply C over V, where C is the speed of light in vacuum and V is the speed of light in a material. So it is that ratio. Now, remember that the materials with higher refractive index will have higher optical density, meaning that light will be traveling much slower. So meaning that this V will be smaller. And then if this V is smaller, and remember this is constant, it means your N, which is your refractive index, will be larger. Like for instance, if you are dividing, say, that speed of light by 1, you will be getting that speed of light. But if you are dividing it by 2, if V is becoming larger, the overall answer now will be much smaller, will be halved. Right, I hope that makes sense. And then let's go back to where we were. We're talking about the use of application of total internal reflection, or the use of optic fibers. So generally it is used in medicine in what we call endoscopes. And then there are different kind of endoscope, but the one that is commonly used here, it is gastroscopy, which is the one that is used to make imaging in the stomach. So an other form of imaging that would not be possible without surgery. So you can see that optical fibers or total internal application of total internal reflection is very important, because you can start to, the surgeons can make an image of the patients in the internal organs without necessarily making operating on those particular patients. And there are also industrial endoscopes. So example of them, it is what we call fiberscope or boroscope. These are used to image interior parts of the machinery. So you don't necessarily have to open bigger machinery. You just use the fiberscope or boroscope to look at that machinery. And then Another form, it is what we call application, it is in spectroscopy. Spectroscopy, it is in here you are able, optical fiber are able to analyze the composition of material that is unable to be placed inside the machine of spectrometer. So without putting the object or the sample into the spectrometer, you are able to then analyze this particular material. Now, in telecommunication, it is used as a media for long-distance communication. That is, even this particular transmission of this lesson, it is using optic fiber. And also the transmission of large data without alteration, like you can watch address from America live, or even from the UK or from Australia, or even from the neighboring country live without alteration of pictures. So you are using, that is an example of application of total internal reflection. All right, let's look at 2D and 3D wavefronts. So what is a wavefront? A wavefront is an imaginary line that is joining points on a wave that are in phase. So it is an imaginary line that is joining the points in on a wave that are in phase. Right, and then we have Huygens principle. It says that every point on a wavefront serves as a source of a spherical secondary wave that moves forward in the same speed as a wave. So it means every point on a wavefront will be generating a secondary wave that moves forward with the same speed as a wave. So that is Huygens principle. Now, what is, we have talked about reflection. So reflection, remember, is the sending back of light when it hits the reflecting surface. Refraction, it is when light changes direction as it enters material of different optical density. So now, diffraction is the ability of wave to spread out in wavefronts as the wave passes through a small appendage or around a sharp edge. For instance, if light is going through like a slight opening, you will be able to see diffraction will be taking place there. Now, the degree of the diffraction is directly proportional to the wavelength. That is, lights with larger wavelength will have high degree of diffraction. And then light, when the slit width is small, where this is W, when the slit width is small, then the degree of diffraction will be high. So the degree of diffraction is inversely proportional to the slit width. So, and then here we are saying lambda is a wavelength, which we should be knowing, and then W is the slit width. Right, so let's consider this diagram here. If you are having a light going through here, it will obviously form a wavefront here. But like, remember, every point, okay, let's just go back to that particular Huygens principle. It says that every point on a wavefront serves as a point source of spherical secondary waves that move forward with the same speed as the wave. So, meaning that if we are having every point on a wavefront, it will serve as a source of spherical secondary waves that move forward with the same speed as the wave. So you can see that if we are having every point here will be serving as a source of secondary wave. So you can see here you are having the main one, which will be serving as a source of secondary wave. But in the process, what is happening here, coming back to diffraction? Diffraction, we have said that it is the ability of wave to spread out wave fronts as the wave move, as the wave passes through a small appendage or around a sub edge. So here, as it is going through a small opening here, the wave is spreading out into wavelets, into secondary wavelets. So you can see that here you are having the main wave and the secondary wavelets are coming here. So it's because light, instead of going straight this way, it will be spreading out into wavelets. So into wavelets. So, and then diffraction will be there to demonstrate the wave nature of light. And then let's try to do the following exercises. I think you will need let's say 5 more minutes to complete this exercise. Then we'll do the solutions together, and then us by past, you should be done. So to answer these 3 questions. Okay, let's try to go to the solution through the solutions together. Right. The first question there was name the phenomenon described by underlined words. So it says light changes direction every time it passes into a new medium. So that should read as the diffraction. Sorry, not diffraction, but refraction rather, because remember diffraction, there has to be an opening. So it should be refraction. So it must be changing direction. So remember that the difference between diffraction and refraction is that diffraction, there must be a edge or a small opening. Refraction, it must be moving from a different into a new different media. Right. The second question was if the refractive index of water is 133 and air is 1, calculate the angle between the light ray and the surface to the water if the angle of refraction is 40 degrees. So what we know here is that we are being told that the angle of refraction is 40 degrees. Now we have to calculate the angle between, we have to determine the angle between, calculate the angle between the light ray and the surface. So we have to calculate this angle, the light ray, between the light ray and the surface of water. So let's see how we go about doing it. First thing is that we have to determine the angle of incident. So the angle of incident will be calculated using this formula here. We know the refractive in option 1. Let's see option 1. Option 1, we can use this equation here from Snell's law, whereby we can now substitute this ray is coming from air to water. So we will have to substitute the refractive index of air, and then the incident angle here is unknown, and then equals to refractive index of water is 133, and then the angle of refraction is 40 degrees. We substitute it, and then we obtain theta equals to 58.75. So after that, we know that this, if this is 58.75, it means here, the normal is making 90 degrees with the surface. Then we have to subtract this 5875 from 90 to get this. So that's what we are doing to obtain, your answer should be 31.25. So the same thing, you can get the angle of incident by saying a refractive index of water equals to angle of incident over sine of angle of incident over sine of angle of refraction. And then you can substitute, you are looking for angle of incident, and then angle of refraction is 40 degrees. Then you substitute this, and then you should be getting your theta to be 58.75, and then you follow the same procedure to get your angle of angle between the surface and the incident ray. And then the next question was, the angle of refraction in glass is 35 degrees. Calculate the refractive index of glass. So to calculate the refractive index of glass, we're going to be saying, using the same formula here. Remember, it is moving from water to glass now. So from water, angle of incidence, it is moving from water to glass. Angle of incidence of glass will be, sorry, refractive index of glass will be 133, And then remember now, where do we get this 40 degrees? We know that the normal is parallel to the surface. So it means, it's perpendicular to the surface. So it means these two normals will be normal at the surface will be parallel to each other. So if these lines are parallel and this is a line, this will be alternating angle, and this angle will be also equals to 40 degrees. So now the angle of incident, remember it is moving from water to glass. Now this will be angle of incident. So sine of angle of incident will be sine of 40 degrees. And then refractive index of glass is unknown, is what we are looking for. And then we're being told that the angle of refraction is 35, so it will be 35. So you'll substitute and get your refractive index of glass to be 1.49. Right. Let's go to the next question. The next question was, draw the sketch below and complete the diagram of a path of light ray from air to water to glass. Show all the values of angles of incidence, angle of refraction, and the normal in each medium. So here, we can then complete this one. Okay, let's just give you 2 more minutes to do this one, and then we'll take it from there. All right, let's try to get the responses to this answer. The first one is to draw the sketch below and complete the diagram of the path of light ray from air to water to glass. Show all the values of the angles of incident, angle of refraction, and normal in each medium. So this is what was expected of you. Sorry about it. Right. It is traveling from air, and we have said this angle, I've calculated it to be 58. That is the angle of incident to be 58.75. This one angle of refraction is 40. The angle of incident here is 40. And then this one, it is 35. So remember that as light is traveling into a more optically denser media, the refracted ray will tend to bend towards the normal. You can see that this angle of incident was 58.75, but here the angle of refraction is now 40. So this angle now becomes the angle of incident as light is moving from water to glass. It was 40, and its angle of refraction is now 35, meaning that the light is moving towards the normal as it is moving towards a more optically denser medium. So you can also try to look at the reverse. If light was moving in an opposite direction, it means as it moving towards the optically less optically denser medium, it will be moving away from the normal, But as it is moving into a more optically denser medium, it is moving towards the normal. Right, and the other question, okay, we have talked about this, and then this we have done. So this is the same diagram. So the other question was, calculate the speed of light through the glass prism if the refractive index of glass is 1.75. Sorry, 1.5. Remember, we calculated it to be 1.49, but here we are asked to use the value of 1.5. So we know that a refractive index will then be given by N is C over V. So refractive index is 1.5, and then speed of light in vacuum is 3 times 10 to the power 8, and then we are looking for speed of light in glass. So it will be 2 times 10 to the power 8 meters per second. Now the question is it possible that total internal reflection of light ray can occur in the above situation? Your answer should be yes or no. So the answer is that it should be no, right? Remember, for one condition for total internal reflection is that light must be moving from an optically denser medium to an optically less denser medium. So here it is moving from into an optically denser medium. So there's no way that total internal reflection can occur. So let's carry on and try to see what else can we quickly do in the next few minutes. Right, and an experiment is performed. Okay, what we'll do is that we will wrap up the lesson now, and then tomorrow we'll start with this activity on this particular experiment, and then we'll take it from there. We'll carry it over to the next lesson. And then now, remember, definition and concept discussed in this particular lesson. And also you must be able to remember the concept, the laws, that is not Newton's law, but laws of reflection, Huygens principle. You must be able to remember definition like what is refractive index, what is angle of refraction, what is refraction, what is critical angle, when does total internal refraction occur. So, and you must use previous DB question papers and papers from other sources, and then remember to practice, and if ever you are stuck, please post some questions so that we can be able to assist you. And remember, you can also get some other sources in this particular, from this particular link. And then I hope you have gained something from this lesson. So let's meet tomorrow, and then we'll be studying ideal gas and thermal properties. But remember, we'll be completing the last section on 3D and 2D of light. And then please, you can get me on this social media. My email address is musala.liburu@gmail.com, and you can always get me on at musaladl, and on Instagram is post_silicon. Thank you.